Welcome to this MOOC on lasers, introduction to lasers. So, today we will introduce the concept of atomic line shape function. A very quick recap, in the last lecture we had seen two level atomic system, where we had seen that this is a two level atomic system here, a two level atomic system where the interaction is between a ground state and one of the excited states, which we call energy level E2. And we have seen that the emission and absorption, the processes of emission and absorption. So, this is indicated here, this process here is representing absorption, that is an atom absorbing a photon making an upward transition, and the rate of emission is given by this B12 into N1. N1 is the number of atoms per unit volume at level 1, and U nu is the spectral energy density. B12 is the Einstein coefficient. The emission comprises of two components here, one that is spontaneous emission and stimulated emission. Stimulated emission is proportional to the rate of stimulated emission is proportional to the spectral density of radiation present. Therefore, at steady state we have seen that at steady state the number of upward transitions must be equal to the number of downward transitions, and we have written this. Therefore, we have this equation, and for a non-degenerate system, after equating this with the black body radiation, we have got the Einstein relations A by B is equal to 8 pi h nu cube by c cube, and A is equal to 1 by TSP, where TSP is the spontaneous emission lifetime. So, spontaneous emission lifetime. So, we have discussed the method spontaneous emission lifetime. And for a non-degenerate two level system, we have B12 is equal to B21 equal to B, and because there is only one A coefficient, we call A21 as A. Now, let us look at this process of emission and absorption more carefully. If we consider the emission spectrum of an atomic spectrum, atomic system, say a two level atomic system, then what we observe is not, if we were to go by this picture here, then we should have got, if we plot frequency versus intensity at that frequency, that is the spectrum I nu versus nu, or I of lambda versus lambda, one and the same. We can write I of lambda versus lambda. This is called the spectrum, the emission spectrum. If we observe the emission spectrum, we get radiation over a range of frequencies. What is shown is a spectrum here over a range of frequencies. But we would expect, if there were only two atomic energy levels at energy E1 and E2, we should have got radiation at one frequency nu 0 corresponding to E2 minus E1 by h. But what we actually observe is a spectrum with a certain width, a range of frequencies. Emission takes place over a range of frequencies. For example, if we look at the emission of a sodium lamp we widely use in undergraduate laboratories. So, we know that it has two lines, spectral lines called the D1, D2 lines. These are easily separable using a grating spectrometer. But if we observe, so normally we observe it as two closely separated yellow lines in the spectrum. But if we observe it with higher resolution, that is, if we enlarge the scale in lambda, then we see that even each one of these lines are comprised of a spectrum, that is, it is spread over a range of wavelengths. So, what is plotted is lambda versus I of lambda, but centered, one line is centered at 5890 angstrom and the other one at approximately 5896 angstrom, which we call as the wavelength of the D1 D2 lines shown here with a separation of 6 angstrom. The point I am making is, if you observe a spectral line of emission from any atomic system, it shows a finite range of wavelengths, emission over a finite range of wavelengths, and therefore, we conclude that atoms interact with radiation over a range of frequencies. Interact here refers to either emission or absorption. Now, let us look at the absorption spectrum. Similarly, if we look at the absorption spectrum of a gas or of a material, then in the transmission spectrum, so what is shown here is transmission. So, as I already mentioned in one of the earlier classes, you have an atomic system. So, there is an atomic system and there is a broadband source. There is a broadband source. Broadband source means we indicate this as a variable lambda source. So, we can vary the spectrum, or it is a broadband source. This comprises of a range of wavelengths passing through this gas. Let us say this is a gas, and then at the output, if we observe the transmitted light. So, this is T standing for transmission. Transmission at the output, then if we plot the transmitted intensity as a function of wavelength, it will be, so this maxima is around 1. So, maximum transmission is 1, but we see a dip characteristic of the atomic system. What is shown is the absorption spectrum, in which we see transmission dips. So, dips in the transmitted spectrum. The dip is because the wavelengths, let us say these are wavelengths lambda 1 and lambda 2, then the atomic system resonantly absorbs around wavelengths lambda 1 and lambda 2. But again, the point to be noted is, it is a range of wavelengths, it is a range of wavelengths over which absorption takes place, which means we again have the same conclusion that atoms interact with radiation over a range of frequencies around any transition. Therefore, the probability that an atom interacts, so atom interacts with radiation over a range of frequencies, and therefore, the probability that an atom interacts with radiation of frequencies from nu to nu plus d nu is given by a function called g nu d nu, which is called the atomic line shape function. And we will discuss about this function g nu. This tells us, this function tells us the strength of interaction. The function tells us, g nu tells us the strength of interaction at the frequency nu, and that is called an atomic line shape function. So, the atomic line shape function, maybe I will show in the next slide, but the mechanisms, this is a topic we will discuss in detail a little later, and the mechanisms that lead to broadening of a line spectrum of an atomic system are called line broadening mechanisms. This topic we will discuss in detail. So, what this statement means is, if you have a 2 level atomic system, then ideally I should have expected one line. If I plot lambda versus intensity, then corresponding to the wavelength here or frequency corresponding to this energy separation, I should have got a line. So, let me just use a different color, and I should have got a line like this, and that is called a line spectrum. I showed you in the previous slide here D1 D2 we showed as lines. So, this is called line spectrum, but when we observed this under higher resolution, the line spectrum showed a finite range of wavelengths, the emission over a finite range of wavelengths. So, the same way, this is a line spectrum, but there are mechanisms which will lead to broadening of this line spectrum into a range of frequencies like this, and these mechanisms are called line broadening mechanisms. We will discuss this. Now, it is these line broadening mechanisms which are responsible for an atomic line shape function. The atomic line shape function gives us the strength of interaction at any given frequency nu, and what it means is G nu d nu, the range of frequencies, the strength of interaction between nu and nu plus d nu is given by G nu d nu. It will become more clear in the next slide. So, let me go to the next slide here. So, the atomic line shape function, again I am just repeating to house the point that atoms interact with radiation over a range of frequencies around any transition. G nu d nu represents the probability that an atom interacts with radiation of frequencies from nu to nu plus d nu, and such a function G nu is called the atomic line shape function. Since the atoms would interact with radiation of some frequency in the entire spectrum, that is, if you take the entire spectrum from 0 to infinity, there will be some frequency with which the atoms will interact, because it has a certain energy difference, and therefore, if we integrate this 0 to infinity, the total probability must come out to be 1. Please see G nu d nu again here is the probability that an atom interacts with radiation of frequencies from nu to nu plus d nu, and therefore, the probability integrated over the entire frequency spectrum has to be 1, and this is called the normalized line shape function. This is the definition of normalized line shape function. The G nu function, which is called the atomic line shape function, is defined as integral 0 to infinity G nu d nu is equal to 1. Now, let us look at this, look at the rate of emission and absorption. We had seen the rates of emission and absorption earlier in the first slide here. So, we have in the last class we had seen the rates of emission and absorption here, and we had taken these as the expressions for emission and absorption, and of course, spontaneous emission here. But now, with the inclusion of the concept of an atomic line shape function, the expressions get modified. So, let us see the new expressions for the rates of emission and absorption. Okay. So, if N2 is the total number of atoms in the excited state, so we are looking at the same 2 level atomic system. One second. So, we are looking at the 2 level atomic system with N1 and N2 the number of atoms. If N2 is the total number of atoms here per unit volume and N1 is the total number of atoms here, then N2 into G nu d nu, by definition of G nu, it means N2 into G nu d nu is the number of atoms always per unit volume atoms interacting with radiation of frequencies between nu and nu plus d nu. So, this is the number of atoms if N2 is the total number of atoms, because G nu d nu represents the probability that an atom interacts with the radiation of frequency between nu and nu plus d nu. N2 into G nu d nu will give the total number of atoms per unit volume interacting with frequencies between nu and nu plus d nu. And therefore, if we integrate this N2 into G nu d nu from 0 to infinity, N2 is a constant. So, N2 comes out and 0 to infinity G nu d nu is 1, and therefore, this is equal to N2. So, the total, it is consistent now, total number of atoms interacting with all the frequencies is the same, N2, and therefore, the rate of, why do we discuss this? The rate of spontaneous emission between frequencies nu and nu plus d nu is A times. Earlier we had the expression just A times N2, but now we are writing between nu and nu plus d nu A times N2 into G nu d nu, because the number is this now. And similarly, that therefore, the total number of spontaneous emissions per unit volume is given by this is equal to A times N2 as before. This is what we had in the last class as before. The total number remains the same, but over a range of frequencies the fractional number of atoms interacting is given by this expression here after we introduced the line shape function. The line shape function had to be introduced to take care of the practical observations that the emission and absorption spectra are spread over a range of frequencies. Okay. Now, the rate of stimulated emission and absorption. So, exactly like the spontaneous emission, the rate of stimulated emission between frequencies nu to nu plus d nu per unit volume, we call it as d gamma 21, is given by B21 into u nu into N2 G nu d nu. Please see, earlier we had just N2. Now, all N2s are replaced by N2 G nu d nu, because this is the number of atoms interacting between nu and nu plus d nu, and therefore, the total number of spontaneous emissions per unit volume is gamma 21 is equal to integral d gamma 21 is equal to integral B21 u nu N2 G nu d nu. Similarly, for absorption, this is for emission. So, similarly for absorption, N1 into G nu d nu is the number of atoms interacting with radiation of frequency between nu and nu plus d nu, which leads to an absorption, and therefore, the rate of stimulated absorption, all absorptions are stimulated. So, rate of stimulated absorption between frequencies nu to nu plus d nu is given by this expression here. Again, as before, you see that earlier we had just N1, now we have N1 into G nu d nu, and therefore, the total number of absorptions is given by the last expression gamma 12 is equal to integral. Now, we want to integrate this. While integrating, again we take care of two practical issues, and that is what we will discuss here. Gamma 21 is given by this, B and N2 were constant. So, we have taken it out. So, u nu G nu d nu. Now, what is u nu? U nu is the spectrum of the radiation which is present in the atomic system or in the medium. What is G nu? G nu is the strength of interaction of the atomic system at a given frequency nu. Now, there are two cases. We separate this into two extreme cases, so that we can understand it more clearly. When u nu is a broadband radiation, for example, in the atomic system here, you inside you have u nu, the radiation which is present here is a broadband spectrum. I have already introduced this word broadband. Broadband means over a wide range of wavelength or frequencies. I of lambda is For example, if you take THL, THL is tungsten halogen lamp, the normal tungsten halogen lamp where a filament, tungsten filament is heated, and this gives out almost a white light like source, and the spectrum, the output varies from approximately from 0.2 micrometer to 2 micrometer with a peak around 0.8 micrometer, that is 200 nanometer to 2000 nanometer with a peak around 800 nanometer, that is in the near infrared. So, this is a wide spectrum of U nu. In the first case, U nu could be a wide spectrum, like have a wide spectrum. In a second case, when U nu is a narrow band radiation, for example, if in this medium, if the laser radiation were to propagate. So, if you were to put laser radiation passing through this, then as we know laser is highly monochromatic, and if you see the spectrum, then it will be very narrow. This is also U nu, the second case U nu, but this is for example for a laser, this is for a laser, and this is for a white light or an LED, a broadband source. So, white light. So, if we categorize these, then we can simplify the integration and the discussion. So, let us see this. First, case 1, when U nu is a broadband radiation, as in the case of thermal radiation. So, gamma 12 is equal to B, this is absorption, rate of absorption per unit volume is B times N1 into integral 0 to infinity U nu d G nu. If we see this figure here, this tells us the spectrum. For example, this is U nu and this is G nu. Why this is G nu is so narrow? Because it is the line shape function characterizing one transition which is centered around the frequency of the laser or nu 0, around the central frequency corresponding to this energy difference, and therefore, it is a narrow spectrum. G nu is a narrow spectrum and this is a wide spectrum. So, in the range of integration, if we look at this integral in the range of integration, so 0 to infinity, which means all of this in the whole range of integration here, the second function G nu is non-zero over a very small range, it is non-zero, everywhere else it is 0, and therefore, we can integrate this function by assuming U nu to be constant, because therefore, this integral will really run over a very, although it is 0 to infinity, the integral will run effectively over a small frequency range, and over that small frequency range, maybe from here to here, we can assume that this U nu changes very little, and therefore, U nu can be taken as a constant and taken outside the integral around nu equal to nu 0. Nu 0 is the central frequency. The value of nu 0 corresponding to that, if we take U nu outside, then we can integrate G nu d nu, and integral 0 to infinity G nu d nu is 1. So, this is 1, and therefore, we have gamma 12 is equal to B n 1 into U nu 0, and using A by B is equal to 8 pi h nu cube by C cube, and we can substitute for B, and we have this expression gamma 12 is equal to C cube by 8 pi h nu cube into 1 by T s p into U of nu 0 into N 1. So, this gives us rate of absorption. Exactly like this. So, it is the same thing illustrated here to say that G nu is a very narrow function centered around. So, what I have shown here. So, this is the central frequency around nu 0, and therefore, the rate of absorption is given by this expression. Now, let us see the rate of absorption for the second case. This is the first case. In the second case, if you use a U nu corresponding to a laser radiation, for example, if the U nu was corresponding to a laser, then we know that laser is highly monochromatic, and therefore, the spectral width of u nu is now a very narrow band source. So, this is a narrow band source, narrow band or highly monochromatic source, narrow band source. Whereas, G nu is the one which is characterizing the transition with a certain finite range, which is measurable. We can easily see this G nu in all the emission and absorption spectra. And in this case, when u nu is much narrower, we can follow the same procedure. We can, in the range of integration, please see, u nu will be non-zero only over a small range, and therefore, over that range we can assume G nu to be constant. So, we assume this to be constant over the range of integration, that is the effective range of integration, and therefore, we take it out the value of G nu at the laser frequency nu L. So, this is centered around nu L, the laser frequency. We take it out and then we have integral u nu d nu, and integral u nu d nu is called u nu, the energy density. What is u of nu? Is the spectral energy density, that is per unit spectrum. And if you integrate over the entire spectrum, then what you get is energy density. Again, just distinguish, u nu is the spectral energy density, spectral energy density. And u nu is the total energy density, u nu. That is why it is integrated over all the spectrum. So, it is shown here again, u nu is energy density, which means total energy per unit volume. If n is the number of photons, so this is beside, if n is the number of photons in the medium, then u nu is equal to n into h nu by V, number of photons per unit volume, per unit volume. So, if n is the number of photons per unit volume, then u nu is n into h nu, energy of one photon is h nu, n is the number of photons per unit, number of photons in the medium, because volume is here, u nu is there. So, this is not there. One second, let me erase that. So, is the number of photons then u nu is equal to n h nu by V. So, this is the rate of absorption in the case of B. This is a practical case in laser physics, because we deal with the laser radiation in the medium. We deal with interaction of a laser radiation or a monochromatic radiation in the medium, and therefore, this is more relevant to us. And with respect to case B, similarly, for stimulated emission, we get gamma 2 is equal to n2 into G nu L into u nu. Instead of n1, we now have n2. So, we have the same expression, similar expression for gamma 2 equal to B times n2 into G nu L into u nu, with B is equal to this. Here. Therefore, to summarize this discussion of rates of stimulated emission and absorption, which now we have upgraded with the inclusion of the concept of the atomic line shape function, is given by gamma 2 is equal to. So, these are the expressions which we will use subsequently to determine the amplification. So, gamma 2 is the rate of emission and gamma 12 is the rate of absorption in a non-degenerate atomic system. You can see that it is almost it is identical except n2 and n1. So, this if we call as W12 into n1, where this entire term which is here is designated as W12. So, it is here W12, then we can write gamma 21 rate of stimulated emission is equal to W21 into N2 and rate of absorption is equal to W12 into N1, where W is called the stimulated transition rate per atom. So, it is per atom, therefore, when you multiply by the number of atoms you get the stimulated transition rate, stimulated emission or absorption. U nu is the energy density associated with the radiation field at nu is equal to nu L. So, here and G nu L, because in the expression also there is G nu L. G nu L is the value of the line shape function G nu at nu is equal to nu L. So, with these expressions we will continue and find out an expression for amplification in a medium by stimulated emission. Thank you.